Okay, hello Block 4. I'm sorry I'm not able to be with you today, but I am here live with Block 7. Block 7, you want to give a shout out to Block 4?
Hi.
Okay, there you go. All right, we are looking at section 2.2, which is polynomial functions of higher degree, meaning higher degree than degree 1, which is linear, and higher degree than degree 2, which we studied in 2.2, which is quadratics. So higher degree, we're going to be looking at degree 3, degree 4, and so on. Claire?
I have a question. Do you
Yes.
get nervous when you're speaking over it?
Do I? No. I just feel awkward wearing it, but I'm okay holding it. All right, your learning objectives. Your learning objectives are to use transformations to sketch graphs of polynomial functions. Stop the talking, please. Use the leading coefficient test to determine the end behavior of graphs of polynomial functions. Find and use zeros of polynomial functions to help sketch graphs. Use the intermediate value theorem to help locate zeros of polynomial functions. So there's quite a bit in this section. The graphs of polynomial functions are said to be continuous. That means they have no holes, no gaps, no breaks. All right? Polynomial graphs also have only smooth, rounded turns, no sharp turns. So for example, you know in a absolute value graph, that's a sharp turn, right? So that would not be visible. You would not see a sharp turn in a polynomial function, right? Absolute value graphs are not polynomial, so we don't want this. All right? Consider functions that have only one term, like 3x to the 5th. If you would graph this 3x to the 5th on the Inspire, how are they the same? How are they different? Let's actually start not with the 3x to the 5th, but let's start with this. Grab your Inspire, and you're going to graph x squared and x to the 4th on the same page of your graph, and I'm wondering what the difference is going to be between the graphs. All right, so how are they different? How are they the same? All right, x to the 4th is skinnier, but flatter at the bottom. Okay. They both are kind of a U shape, but only x squared would be considered a parabola. X to the 4th is not considered a parabola, but it's still a bowl shape. Okay. All right. So when you graph these, x squared, here's the graph, and if I do x. So here's x to the 4th. It is flatter at the bottom, but it rises more steeply. All right, that's how I would define it here. What about x to the 3rd and x to the 5th? Try those on a different page. All right, so x to the 3rd, if you're graphing that one, the general shape looks something like this, like a squiggle. Oh, pardon me?
What is that called again? Squiggle.
The technical term is squiggle. Just kidding, Block 4. Okay, and then, so what's the difference about x to the 5th?
It does the same thing as x to the 3rd.
All right, so it's a little bit skinnier, but it is flatter near, so something like this. Okay, notice the higher the power, the flatter the graph is near the origin. Okay, so how would you describe, just like the warm-up you had today, describe the transformation and sketch the graph. So let's say we have opposite of x plus 5 to the 4th. How would you describe the transformation from the parent graph, which is y equals x to the 4th? Okay, so this negative here is going to be reflecting our graph over the x-axis, and what about the plus 5?
Move it to the left.
All right, it's going to shift to the left 5 units. So if I shift this to the left 5 units, and then I flip it it's going to look something like this. Everybody agree?
Yes.
Does that look all right? Okay. Um, okay, what about this one? 1/4 x minus 3 quantity 4. Hands, please. Hands, please. Gray.
Is it a vertical shrink?
All right, this 1/4 here is going to mean it's a vertical shrink. And what about the x minus 3?
3 units to the right.
Shift to the right 3,
Before.
and then up 1. Are we okay with this?
Wait.
That makes it shift up 1. Because that's outside of the x to the 4th part. Okay, so in general, I'm going to ask you to make a little page in your notebook. I would actually ask you to kind of turn your notebook this way. All right, so you've got enough room to make these graphs. All right. You might want to start a new page, turn the page, make it sideways so you have enough room. And we're going to be graphing polynomials in general form. And we're going to be comparing the degree and so on. So we're going to make 2 graphs for each degree. This is going to be a degree 1. This is going to be degree 2 graphs, degree 3, degree 4, degree 5, and degree 6. Okay? You already know that if it's a degree 1 with a leading coefficient positive, remember these are your leading coefficients here. So this one in general would be y equals ax plus b, or you could use mx plus b, but I want to be consistent with a, b, c, d, and so on. So if we're talking about a degree 1 polynomial function, if the leading coefficient's greater than 1, then that graph is going to be looking like what?
Straight line.
Straight line. Lines are always straight. So how would you describe it?
Oblique.
Doesn't it start low, end high, something like this? Yes? You with me?
No.
Okay. And then what if the leading coefficient was negative? Starts high, ends low. So it looks something like this. A linear function, but with a slope that's negative. So it's going to be a falling line. All right, what if we are talking about degree 2 polynomial function? So degree 2 polynomial function would be something like y equals ax squared plus bx plus c. If my leading coefficient is positive, what's the graph going to look like? A U shape. A parabola, is it going to be opening up or down? Opens up. So here, this graph is going to be opening up. What about if the leading coefficient was negative?
Down.
Then it's a parabola that opens down, something like this. All right, what did we say about a degree 3? It's a squiggle, but hang on a second. Before you draw that squiggle on your paper, if I asked you to graph something like y equals, and again, the general form for this would be y equals ax cubed plus bx squared plus cx plus d. You with me? Right? So when you add in all that extra stuff, like let's make it a 2x cubed minus 4x squared plus 3x minus 1, type that into your calculator. Let's see if we're getting anything interesting shape-wise.
Pull that back up.
Still squiggle. 2x raised to the third.
Wait, you're in the.
Ah! Minus x squared plus 3x minus 1. I don't even know if this is the same one I gave you. It looks like this, right? But what if I change this minus to, let's say, a plus? Still not doing much. What I want you to notice, and I'm not being very successful at getting you to notice this, there we go, is, shh, focus please, is when you have a degree 3, it won't always just be that standard squiggle. It might actually have like a local maximum, as we would call it, and then start heading down and get to a local minimum and then start heading back up again. So the graph that I want you to put on your notes page here is that type of graph that it's going to start low, have possibly a squiggle like this in it, and then it's going to end high.
So that would not be a function.
It is a function. What's wrong? Why? It's still going to pass the vertical line test.
All right.
Right? Its inverse is not going to be a function because it won't pass the horizontal line test. All right, and likewise, if the leading coefficient is negative, it's going to start high and end low. So a degree 3 is going to look something like this. Are we okay with this? All right, let's try a degree 4. So if we try a degree 4 polynomial function, just making one up here. Let's see. If I have something like x raised to the 4th plus 3x cubed minus 2x plus 1, not again, let's see, plus 2x, I'll just leave out a squared, let's see what happens. Interesting shape. Okay, that was a -1. It's not as interesting a shape as I was hoping for, though. Let me add in, let's say, a plus 5x squared term.
Well, you didn't do anything. Oh, there we go.
That's still not what I'm looking for. Just playing around here. Let's make this, I'm going to make this like a -3x to the 3rd. Still not what I'm looking for. Let's see, what if I make this a minus here? Not exactly what I was looking for. How about if I make the x to the 4th negative?
Wait, I just, squared up, I'm with you. I was telling it actually does work.
All right, so I tell you what I want you to notice, and I'm not sure if I'm making it clear, is that if you have a degree 4, the polynomial function is y equals ax to the 4th plus bx to the 3rd plus cx squared plus dx plus e, if you will. You with me? The general shape is going to be like this. It's going to be like a W kind of shape, where it's going to start high. It's going to start high and it's going to end high, but it might have these squiggles in between. And as I just showed on this one that I just did, that's this one. This one is starting low. It's got some little squiggles in it, and it's ending low. So it's almost like an M kind of shape. And that's what I would like you to be thinking about when you are, whoops, there we go. So it starts low. Each one adds a curve, exactly, or has the potential to add a curve. So a degree 5, oh man, I was trying to color code these two. Not too late. So this one, like this, here, like this, here, okay? And then when we get to degree 5, it's going to still start low and end high, but it might potentially have an extra squiggle in it. So it might look something like this. Leading coefficient negative, it's going to start high, maybe have that many squiggles in it, and end low. All right. Degree 6, we're back to the same start high, end high, but it might have an extra squiggle in it, like this. And for degree 6 with leading coefficient negative, it's going to start low, end low, but has the potential for having this many squiggles. Will it automatically have that many? No. If I just ask you to graph f of x equaling x to the 6th, just by itself, that's not going to have all those squiggles in it. It's just going to look like a very flat parabola kind of shape, right? All right, it's only the extra terms that give it that added flavor, if you will. Okay, so let's talk about the leading coefficient test. So when I give you the leading coefficient test is when I give you a function, for example, f of x equaling negative 3x to the fifth minus 4x plus 7. The leading coefficient test that you're going to be using is going to be able to tell whether this function starts low, ends low, starts high, ends high, or what. So what do you think it's going to do?
Start high. If it's odd, it starts low and ends high. No, so it starts high and ends low.
So I want you to be noticing that this is notice that this is a degree 5, so we're talking about these pictures here, right? You with me? And the leading coefficient is negative, so that means we're really talking about this picture right here. So it should start high and low. It's a lot of highlighting. So our leading coefficient test will say it starts high and ends low. Everybody agree? All right. So what I want you to do, though, is I want you to make some generalizations about these pictures that we have just drawn. So I want to know what happens for every time, for example, when n is odd and the leading coefficient is greater than 0. Well, that's not the one I started with. I started with this one, so let me get this one up first. I gave you an example like this, didn't I? This example right here, yes? It's an example where n, which is the degree, is odd, and the leading coefficient is negative. So we said, hey, it starts high and ends low, but you know what? You are sophisticated mathematicians, and you can use notation that will be an intelligent way of writing starts high, ends low. All right, the intelligent notation that you're going to be using is this. F of x approaches what as x approaches negative infinity. What that means when you see as x approaches negative infinity, when you see this part right here, I want you to be thinking as x goes further and further to the left. So on your graph, which we said was, we were liking, we're liking this graph right here, correct? That's the one? So as x goes further and further to the left, what's happening to the function? It's going up or down? It's going up. So we're going to say that the function itself is heading towards positive infinity. So what we're going to write here is f of x approaches positive infinity as x approaches negative infinity. Then f of x approaches what? As x approaches positive infinity means as our graph goes, as x goes where? As x goes to the right, what's happening to the function? As x goes to the right, where's the function going? It's heading down, 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 right here. So we're going to say as f of x approaches negative infinity as x approaches positive infinity. Are we okay with this? All right, so what about if n is odd, but the leading coefficient is positive? So now we're talking about odd degrees, and the leading coefficient is positive. So in my graph here, I'm talking about this one. Degree is odd, right? And leading coefficient is positive. I'm talking about this one here. That's an odd degree with a leading coefficient positive. I'm talking about this one here. You with me? So what's common to all three of these graphs? They all start low and end high. So when you write that, I'm going to just jot that here. Starts low, ends high, right? But how are we going to answer this? As x approaches negative infinity means as we go further and further to the left, what's happening?
They match. The infinities match.
So as x goes to negative infinity, as we go further and further to the left, the function's going where? Down. So we're going to write f of x approaches negative infinity. Agreed? And as x approaches positive infinity, which means as we're going to the right, This one was to the left. As we go further and further to the right, what's happening with these? As we go further and further to the right, what's happening to the function? It's going up, so we're going to write that the function is approaching positive infinity. Agreed? All right, so I'm going to ask you, we've done 2 of these, I'm going to ask you to do the other 2. All right, and that is, that's not what I want to happen. As n is even, if you've got an even degree and the leading coefficient is positive, how would you answer or fill in the blanks here? And what if the degree is even and the leading coefficient is negative? So if the leading coefficient is positive and the degree is even, take a look at your graphs that you drew and fill in the blanks here. And then what about if your leading coefficient is negative but your degree is even? I'm going to give you 30 seconds and I'm going to call on you to tell me what to put in these blanks. Okay, what did you say for this? For n is even, degree is even, and the leading coefficient is positive. Katie? So if the graph, for example, for a degree 4 and leading coefficient looks something like this. So as we go further and further to the left, that means as x approaches negative infinity, you said the function is heading to up, positive infinity. And then what about as x approaches positive infinity, which means as we go to the right, then the function is heading where, Nate?
Negative.
Do people agree? As we go further and further to the right, Nate, this graph is going up.
Oops.
So it's heading to positive infinity. All right, what about this one? Where n is even, but the leading coefficient is negative. So for example, I'll just use a parabola. This is a degree 2, that's an even degree, right? And the leading coefficient's negative. So as we approach negative, as x goes to negative infinity, that's this part, the function is heading where? Down. So we're going to write negative infinity. And what about as x approaches positive infinity, where's the function heading here, Riva? Does everyone agree? All right. Okay, so those are the leading coefficient tests. All right, so I do need you to have some way in your head of remembering these. The question for block 4, you might not have heard it, is will I expect you to be able to hand graph these? And I guess the question is, I will expect you to be able to graph some of it. In other words, I expect you to be able to identify is going to start high, and start low, end low, whatever it is. You know what I mean? I also am going to expect you to be able to identify the y-intercept and plot that accurately. I also need you to be able to find the zeros of the function that we're going to be talking about today and to plot those. The zeros of the function are the same as the x-intercepts of the graph. All right, so there are some things that I would ask you to do. And also we can find turning points and so forth. Okay, so do we need to go over these or are we good?
Good.
We're good? Okay, then I'm going to skip over this.
Plus
1255.
55.
Okay, so let's talk about zeros as I was just mentioning. Zeros of a polynomial function. A function f of degree n has at most n real zeros and n minus 1 turning points. So that means that if your function, let's say, I'm just going to use as an example, let me just say as an example, let's say we've got a degree 3 function. All right, the degree 3 function has at most, degree 3 function has at most, how many zeros? 3 zeros. And how many turning points? And at most, 2 turning points. Do you understand what we mean by turning points?
I do.
So if our graph for a degree 3, our degree 3, for example, might look like this. How many zeros does this function have? 3 because it has zeros here, here, and here. The zeros of the function are the same as the x-intercepts of the graph. But if this graph was a little bit higher up, now how many zeros does it have? Now how many zeros does it have? Still 1. Because this is still going to be heading down, right? So, and it might have 2. How many turning points does it have? Turning points are going to be these relative minimums and relative maximum points, right? That's why at most it's going to have 2. All right, the turning points are called the relative minima and relative maxima. They are points where the graph changes from increasing to decreasing or vice versa. So this point right here would be a relative maximum because it's changing from increasing to decreasing. This point right here would be considered a relative minimum because the function's changing from decreasing to increasing. Those are called turning points. All right, finding zeros of polynomial functions is one of the most important topics in algebra. It is closely related to factoring and finding x-intercepts. What is, first of all, the real zeros of a polynomial function. If f is a polynomial function and a is a real number, then the following statements are all equivalent. So this is kind of nice. This is kind of like wrapping up a bunch of things in algebra with one like ribbon, all right? Because we're tying a bunch of things together. First statement is that x equals a is a zero of the function f. If that's true, that x equals a is a zero of the function, then we could also say that x equals a is a solution of the polynomial equation f of x equals 0. So we are now, so far we've related zeros of a function. Zeros relate to functions as solutions relate to equations. You with me? A zero of a function, same as a solution of an equation, right? These things are related. And this statement is also equivalent. If x equals a is a zero of a function, then x minus a is going to be a factor of the polynomial. All right? X minus a is going to be a factor. And lastly, a comma 0 is an x-intercept of the graph. So we are relating. What are we relating? We are relating zeros, solutions, factors, and x-intercepts. These are all closely tied in and related to each other. All right? These statements are all equivalent.
What is it? What's the x?
X minus a, that quantity, x minus a, is going to be a factor of the polynomial. So I think we're going to hammer this home with this example so you'll understand what we're talking about. Make 4 statements regarding the function f of x equaling x squared minus 10x plus 25 that match the statements above. All right, I don't think I have anything on here. Oh wait, maybe I do. All right, so first of all, would you agree that if we wanted to find the zero of this, if I want to find, I'm on step 1 here, what's a zero of this function? Well, can we factor this? All right, what's a factor? X minus 5 times x minus 5, agreed? Right? So I could write my function this way, and if I set these equal to 0, all right, then I get x equals 5 all the time. So x equals 5 is a zero of the function, right? 5 is a zero of the function, but I could also say that 5 is a solution of, that's not the equation I wanted, is it? Where'd that come from? Oh, wasn't it supposed to be minus 10x plus 25 equals 0? Okay, and same thing here, minus 10x plus 25. All right. So our 4 equivalent statements for this problem would be 5 is a zero of the function, 5 is a solution of the equation x squared minus 10x plus 25 equals 0, x minus 5 is a factor, but we already saw that here of the function, and 5 comma 0 is going to be an x-intercept. All right, that's how we're tying all these words together: zeros, solutions, factors, and x-intercepts. Questions on this? Okay. So let's take a look at an example. All right, let's take a look at this example. Find all the real zeros of f of x equaling x cubed minus 12x plus 36x, then determine the number of turning points. So if we have x cubed minus 12x plus 36x, can we factor this? What goes in all three of these? X. So I can factor out an x, and I'll have x squared minus 12x. Let's make that a squared. I bet it was supposed to be a squared. I'd have to look at my notes. So then would this be 12x like plus 36? All right, can this thing factor?
Yes.
What does that factor into?
X minus 6 minus x.
Okay, so here's my question for you. What would be the zeros of this function? 0. All right, well, let's chat for a minute about this. Let's back it up. What was the degree of this? What was the degree of this polynomial?
3.
Degree 3. So guess what? There's going to be 3 zeros. We're going to learn that later, but I'm just going to give this away right now. That if you've got a degree 3 polynomial function, there are going to be 3 zeros. They may be real. They may be imaginary. No, we haven't talked about imaginary yet. They may be repeated, but there will be 3 of them. So what are our 3 zeros for this? Perfect. 0, 6, and 6, right? Because this is really x times x minus 6 times x minus 6. Set each of these equal to 0 and solve. You with me? So there's 3 zeros. So what about the x-intercepts? What are the x-intercepts? Yeah, 6 comma 0 and 0 comma 0. Agreed? So what I want you to do is type this in to your calculator, and let's see what happens. First of all, while you're typing this in, I'll just ask you, is this graph going to be starting high, ending high, starting low, ending low? Can you use the leading coefficient test? Starting low, ending high. Do people agree? Yes, because it's an odd degree, and the leading coefficient is positive, so it starts low, ends high. So the point is, I'm going to try and get this graph, this shape, starting low, ending high, but I need it to go through 0 and 6. You with me? How is that working for you? Yes? So it starts low. Does it come up? Here's my question. Does it look like this and like this? Or does it look like this? Like this? The first one?
Yeah, but it's really high. Way high. It like almost high.
All right, well, yeah, and I'm not as worried about how high it's going as I'm not as interested in how high it's going, but I am interested in, does the graph cross at 0, or does it kind of bounce off of 0? It's crossing through. So it's crossing through at 0, and then is it crossing through at 6? It's bouncing. All right, so we want it to cross through at 0, and we want it to bounce at 6. Why do you think it's doing something different at 0 than it's doing at 6? Is there a difference in the function where we have 0 and where we have 6? 6 is occurring twice, right? Because 6 occurs as a 0 twice, that means that x-intercept is going to be, the graph's going to bounce at that point. All right, and we're going to get to that also, where the degree, if the degree on that factor is even, it's going to bounce. If the degree is odd, it's going to cross through. All right, so sketching the graph of Did I answer everything we were supposed? Oh, determine the number of turning points. How many turning points did we have for this graph? 2, right? We had a maximum here, and this looks like this point right here is a minimum, right? It's a 0 and a minimum. Okay, on to this one. Sketch the graph of f(x) equaling 2x cubed minus 6x squared. First of all, what's the degree? Degree 3. What's the leading coefficient? 2. So leading coefficient is positive. Agreed? And what are the zeros of this function? Can you factor it and find the zeros? What can I factor out? 2x squared. So what's going to be left? X minus 3. Do people agree with that? All right, so that's our function. And that means my zeros, if I set this equal to 0, and I set this equal to 0, what are my zeros? 0. It's degree 3, though, so I'm looking for how many zeros?
I think that'd be
0, 0, and 3? Why? Because we've got x times x minus 3, right? Agreed? So that means my zeros, when I set these each equal to 0, I'm going to get 0, 0, and 3. True? Is that okay? I mean, I could squeeze the 2x in here if you'd like and make that a 2x, but when I set it equals 0, I'm still going to get 0. Okay, so where are the x-intercepts? 0, 0, and 3, 0. Everybody agree? So before you, don't type it in, before you do this, I'm asking you, without a calculator, can you sketch a halfway decent graph of this? Does it start high, end high, start low, end low? What's it doing? Starts low, ends high. Do people agree? Yes. All right, and it's going through 0, 0, and 3, 0. So I know it's starting low, so it's coming up like this, right, from here, and it's going to end high. Agreed? And what's it doing in between? Bouncing at 0?
Yeah, like a pool. No, just
Like this?
Yeah.
Something like that?
Keep going and then.
Or would it?
It should be bouncing at 0 because 0 occurs twice, right? An even number of times. And it's crossing through at 3 because that occurs an odd number of times, just once. All right. And I'm skipping that one. Okay, let's talk about the intermediate value theorem. All right. It is, but I planned out the rest of our year. That's what I did on Friday, my day off, and we gotta make tracks through 2 and get to 3, and we should be okay. But all right, intermediate value theorem. Given the graph of a polynomial function that passes through the point 2, 1 and 4, 5, will there be an x value that we could plug into the function so that the function would equal 4.5? I'm asking you, for example, let's change this. All right, you like that? No?
Not at all.
How about this?
There we go.
Okay, so I'm asking you if this height of this horizontal line is at, a height of 4.5, you with me? Is there going to be an x value that can give me that height? Is there going to be something here in between? This is 2, right? And this over here is 4. Is there going to be some x value that I could plug into the function so that my output would be 4.5? The answer is yes, there is. Because this is a continuous function. Remember, we said that at the beginning of this lesson. Polynomial functions are continuous. That means they're going to take on every single value between one and another ordered pair. So the answer is yes, there is. There will be a number, c, so that f of so that f of c is equal to 4.5, and the c will be found in that interval. Focus, please. Will be found in that interval from 2 to 4. Okay, so that's an example of the intermediate value theorem. Here's what the actual theorem looks like. Theorems like this will be quite commonplace in calculus. All right, theorems that have a lot of words and some symbols and so forth, and you're going to need to make sense of it. All right, the intermediate value theorem says let a and b be real numbers such that a is less than b. If f is a polynomial function, so that f of a is not equal to f of b, then in the interval from a to b, f will take on every value between f of a and f of b. So in this intermediate value theorem, relating this theorem back to this example, right? Let me shrink this up. So in this example, the intermediate value theorem, the a was really 2, and the b was 4, right? So we're saying f of 2 was not equal to f of 4, right? Because what was f of 2 equal to? F of 2 was equal to 1. What was f of 4 equal to? 5, right? So they were not equal. That's good. That's fine. And that means that in the interval from 2 to 4, in this case, the function is going to take on every value between 1 and 5. So you can get any value between a height of 1 here and a height of 5 here.
What's the purpose of finding?
The purpose of this theorem is to help you find zeros of the function. So take a look at IVT, intermediate value theorem. Use the intermediate value theorem and the table feature of the Inspire to find intervals in which we are guaranteed to find a zero. So we're looking at number 87 together from 2.2, and the function says use the intermediate value theorem and the table feature to find intervals, blah, blah, blah. So it's 3x to the 4th plus 4x cubed minus 3. Number 87 from this book. On your calculator, on a graphs page, I am typing in, what was it, 3x to the 4th? Plus 4x to the 3rd? Minus 3. All right, this is number 87 from section 2.2. There's our graph. It starts high, ends high, right? It's a degree 4 leading coefficient positive, so we're not surprised by that. Do Control T, pull up the table. And what you see here is, notice if we try, let's go back a little further. If I plug in -3, I get 132. F of -2 is equal to 13. F of 1 is equal to -4. So what just happened in between -2 and a -1? What just happened? We went from a positive value to a negative value. You with me for the function? Because f of -2 was positive, equals a positive number, and f of -1 was a negative. So what had to have happened between -2 and a positive 1? What happens in this interval? A zero of the function. Thank you, Mara. Has for Mara. So -2 is up here at 13 somewhere, right? But -1, f of -1 is down here at -4. So my graph is looking something like this. You with me? So somewhere in between -2 and -1, it must have crossed the x-axis. Does that make sense? All right. So that is the intermediate value theorem at work. All right, I'm going to stop here. Your homework assignment will be on the website, so check that, and we'll see you next time.